So today we're extremely pleased to have one of my one of my Cornelian colleagues, right? Because still, once a Cornelian, you're always a Cornelian. He told me he's one floor above exactly where my former office was, right? Something
exactly,
like that. Yeah. Yeah. So we're very pleased to have Andrew Gordon-Wilson, who will speak on Bayesian Generative Adversarial Networks. So Andrew did his undergraduate degree at Vancouver, did his PhD at the University of Cambridge with Zubin Garamani. He joined CMU and worked with Alex Molla. And so he joined Cornell in Operations Research and Information Sciences, I believe last year. And his work is on all aspects of machine learning, including lots of innovative approaches to Gaussian processes. But today he will speak on Bayesian GANs, an extremely important topic. So we're looking forward to your presentation.
Thanks so much. It's a great honor to be here. Thanks for the invitation and introduction. So this is recent work that I have with Younes Sachi from Uber AI Labs at NIPS. So we presented this at the NIPS conference in December a few months back. It's something I'm sort of very excited about in machine learning in general. Generative adversarial networks have been all the rage. They can learn rich distributions over images, audio, and sort of other really high-dimensional natural signals, which have been hard to model using traditional approaches, which I've denoted as an explicit likelihood in this first bullet here. In this work, we introduce a Bayesian GAN, which requires minimal human intervention, so you can get it working without a lot of fiddling, and provides really powerful semi-supervised results. So though classical GANs have had a lot of success in modeling images, audio, etc. To get them to work, quite often we need to intervene quite a bit, and this is a little bit at odds with the purpose of machine learning, to build systems and algorithms which can learn and make decisions without a lot of intervention. So that is one of the issues that we've attempted to address. It also has various other pathologies which can be addressed quite naturally from a Bayesian perspective. The semi-supervised learning results are something that I'm very excited about. In particular, we found that with just 1% of the labels on many of these image classification benchmarks and just having everything else be unlabeled, we were able to match state-of-the-art performance compared to fully supervised approaches using 100% of the labels. So this is a really practical sort of direction for GANs in general. It's a way to quantify how well they're working, and it's a way to do something really practically useful. And it really shows how much we can learn in an unsupervised setting. Also, although it's not the main focus of this talk, a lot of what has enabled the Bayesian GAN to get such results has been an inference approach called Stochastic Gradient Hamiltonian Monte Carlo, Stochastic Gradient HMC. And so I think that this style of inference will have big implications for Bayesian deep learning in general. And I'll argue why I think Bayesian deep learning is generally an exciting area. And I think a lot of the techniques that I discuss in this talk aren't necessarily very specific to this particular model. They're ideas that you can apply quite generally when you're developing your own models. So one of the goals in this talk will be to have you, by the end, actually understand what this figure means. So we'll see this come up a few times. Before we get into the details of GANs and Bayesian GANs, a bit more high-level motivation. So why do we care about unsupervised generative modeling? Well, as I mentioned earlier, one of the ambitions in machine learning is to develop algorithms which will eventually act as intelligent agents that don't really need us, in a sense, to be able to learn and make interesting decisions. And a lot of the learning that we do is unsupervised. So we don't typically have a labeled training set of horses and not horses, and then we learn to classify it somehow. A lot of what we're doing is, a lot of the learning we do comes without labels. So this is something that is thought to be very foundational to this ambition of doing machine learning. But more specifically, anything we do in unsupervised learning will have a bunch of immediate practical consequences. For example, GANs have been used to simulate possible futures for decision making and reinforcement learning. As I've mentioned, you can do semi-supervised learning, and that's an application that I'll focus on in this talk. A lot of startups have been revolving around things like image super resolution, in-painting, various types of video and image extrapolation problems. If you have a sequence of frames in a video, can you extrapolate what's going to happen next? And these are questions we can kind of immediately get to work on with some of the advances that have been provided by this class of models, GANs, and one other class of models called variational autoencoders, VAEs. In fact, I got interested in GANs after Jan LeCun visited Cornell, and in the CS colloquium, he proclaimed that GANs were the most significant new development in machine learning in the last 10 years. I'm not sure whether this claim is true, but it was enough to get me to read the paper at least, and I think that they are quite exciting classes of models. Of course, there's still a lot more work left to do, so it's not like GANs have solved the problem of generative unsupervised modeling. They are just a big advance and somewhat of a new direction. So that I think GANs in particular are somewhat of a fresh idea from which we can really build quite interesting models in this space. And this space of modeling is really foundational to the ambition of doing machine learning. Okay, so what are GANs? So GANs implicitly perform what's called density estimation, whereby we have a rate generator G, which proposes samples from a data distribution, attempting to fool a discriminator D, and learning takes place through an adversarial game between G and D. So we'll unpack this a bit more in the next few slides. And as I've mentioned, GANs are particularly good at learning to sample from distributions over images, which has been practically an intractable problem prior to these types of models. Before I get into the details of how GANs work, let's first consider a more classical density estimation problem. So this is kind of a statistical machine learning sort of classical example. So we can suppose that we have a bunch of observations, in this case y1 up to yn, drawn from some unknown density, and our learning task is to try to estimate that density. So conventionally, we would start with what's called an observation model. So we'll assume that those points have been drawn from, say, a mixture of Gaussians. And the learning task is to estimate the parameters of those Gaussians so that we can model this density that the points have been drawn from. And so here's our observation model. From this observation model, we can formulate a likelihood. And our task is to learn all the free parameters. So the means of the two Gaussians in this case, their variances, and the weights of the mixture. Now, the reason partly that this is a classical example is because it's a pathology of what's called maximum likelihood density estimation. So one of the Gaussians in this case is free to disperse its mass across all the points, and the other will collapse itself onto one of the points, achieving infinite likelihood, but not providing a density estimate that we would really believe. We probably don't believe that one of the points that we've observed has been generated just by a delta function centered on that point. That's certainly not something that's going to generalize to more data. And so one way to remedy this pathology is to do regularization, where we introduce some kind of regularizer which goes to 0 faster than the likelihood goes to infinity for these pathological settings of the parameters. So that's sometimes called map estimation. An alternative approach instead is to do full Bayesian inference, where you have a distribution over the parameters, and then you have your density estimate given those parameters, and you do what's called this Bayesian model average. So you have the density given some setting of the parameters, weighted by the posterior probability of those parameters given the data. And so from that perspective, actually the point mass solution isn't necessarily tragic. In fact, it's okay if it's a couple solutions in some uncountably infinite set, or sorry, uncountably infinite set of solutions, as long as it doesn't have 100% posterior probability. So as long as we believe it might be possible, then fine, represent it in the model average, but also represent the infinitely many other models which could have possibly generated the data. And from this formulation, we can actually use infinite mixtures of Gaussians even, which are very flexible. They can model any kind of density that we like, in conjunction with very vague priors that don't have strong preferences for any values of these parameters theta. So the Dirichlet process mixture model is a famous example of one of these infinite Gaussian mixture models. And so the Bayesian formulation is sort of very natural in this case, we're using flexible models which don't have these classical overfitting pathologies. Now, GANs follow a different approach. Instead, they think about trying to generate samples from this distribution of interest. And to start to do that, first one samples several variables, z1 up to zn. And typically, these are sampled from some pretty vanilla sort of distribution, like a uniform distribution or a simple Gaussian distribution. And then we transform those samples through what's called a generator, which we're labeling G here. And the generator will have its parameters, theta G, to get as output samples, candidate samples from this sort of data distribution of interest. So this is just the forward model we're defining here. We sample noise, we pass that noise through some kind of function G, which has its own parameters, theta G, and out we get candidate data samples. And so G could really be anything. Typically, it's specified as a neural network, and theta G are the weights of the neural network. And the learning task is to try to learn the theta G that will give us good samples. And we could understand this a little bit from a statistical perspective through a procedure called inverse uniform sampling. So you may have heard of this. You can start by sampling from a uniform distribution, and then you pass those samples through some inverse CDF of interest, and you get samples from that other distribution of interest. So if I wanted to sample from a Gaussian distribution, I could start by sampling from a uniform, and then pass those samples through an inverse Gaussian CDF. Then I would get samples from a Gaussian distribution. So what this means is that if G is flexible enough, if it has sufficient capacity, then it will be able to represent the right sort of CDF inverse CDF transformation to sample from some distribution of interest through the correct setting of its parameters theta G. So if it's a flexible enough function approximator, it can approximate that transformation that'll get us samples from the data distribution that we want to model. So we know that in theory, it's possible to find the right theta G. The next question is, how do we find that setting of theta G? I said CDF, inverse CDF composition. So if you transform something that isn't uniform through its own CDF, then it'll become uniform. And then you can go and do your inverse CDF mapping to get a sample from a distribution of interest. So this slide is largely to set up the notation we'll be using throughout the talk. We have the generator here, G. We have its parameters, theta G. That's what we're trying to learn. Z is stuff in sort of the noise space that we start with, that we pass through G to get samples in the data space, which is denoted by X here. So visually, we start with a bunch of noise, pass it through the generator, we get images. In principle, the generator is specified not only as a neural network, but as something called a DC GAN, a deconvolutional neural network. So you start with some low-dimensional vector Z in noise space. You pass it through several sort of inverted convolutional layers, and you'll get an image as output. And so in slightly more detail now, we'll start by having our generator propose candidate data samples, and then we have this other model called a discriminator. And it has access to some training data set, which has presumably been sampled from the distribution that we're trying to model. So that training set could be like the Y1 to Yn we had in the first density estimation example. And the discriminator is actually pretty simple. What it does is it's just a binary classifier. It takes as input a sample, and it outputs the probabilities of two class labels, from the generator and not from the generator, from the data distribution. And so, in fact, you could just view this as a scalar output from 0 to 1. The probability that its input comes from the data distribution of interest. And so it's trying to learn its parameters, theta D, such that it labels samples from the generator as from the generator, and samples from the data distribution as from the data distribution. So the generator tries to update its theta G to fool the discriminator. It wants its outputs to have outputs from the discriminator that are close to 1. It wants the discriminator to think that its samples come from the data distribution of interest. On the other hand, the discriminator is kind of fighting the generator, and it wants to call out the samples from the generator. And in the original paper, they have kind of a fun analogy where the gang, you could view a generator kind of like a gang producing counterfeit currency, and the discriminator like the police. And over time, the gang improves its mechanism for generating counterfeits through feedback from the police. But the police also kind of refine their methods for identifying counterfeits by seeing more and more attempts from the gang, until eventually the gang is eventually generating actual currency. And we can prove, and we will shortly, that if G and D have enough capacity, if they're flexible enough, then samples from G will actually converge to samples from the data distribution that we're trying to model. And although for this proof to hold, we rely on capacity, the procedure works in practice because of the powerful, what are called inductive biases, typically, in the generator and discriminator. So originally, I started by presenting this as a classical density estimation problem where you specify a likelihood and you try to learn the parameters in the likelihood. And I even said that if you have an infinite mixture of Gaussians, you can estimate any density to arbitrary precision. The follow-up then is, why don't we use that model if this is all about capacity? And the answer is inductive biases. So from the perspective, for example, of a mixture of Gaussians, two images will be considered close together if they're close in, say, the distances of their pixel intensities. Whereas here, basically, we're using a convolutional neural network for G and D, and this has kind of baked into it all sorts of statistical properties which are very good for modeling images. So notions of similarities, for instance, between images, having things like translation invariance for classification sort of already part of the way that model was constructed. So in practice, really what makes this work well is the fact that G and D are convolutional neural networks. Okay, so here we have a visualization of the training procedure. We start out with the data distribution we're trying to model, given by the black dots. We have the distribution that's implicitly represented by the generator, shown in green. And in blue, we have the outputs of the discriminator. So first, we sample from this distribution in Z space. It's a uniform distribution, so here the points are roughly regularly spaced. Because G has most of its density over in this region of space, most of the X samples will be concentrated over in that region. And the discriminator will be able to quickly update and say, no, those samples aren't probable, because those samples are pretty far away from the actual data distribution. So it's very easy for this blue curve to shrink down to 0 in that region where the data were initially sampled from the generator. The generator then gets that feedback and says, oh, I need to shift my distribution over to this region of space closer to where the black dots are so that I generate more convincing samples that will fool the discriminator. And eventually, the generator will actually be sampling from the data distribution and the discriminator will be confused. It'll just be outputting a half. So this is the exact objective that was proposed in the classical GAN paper. We have an expectation over the log of the discriminator here, and then we have an expectation over samples from the generator, where you have log 1 minus the discriminator operating on the generator. And so the discriminator wants to maximize this objective because it wants to say that samples from the data distribution come from the data distribution. So it wants the outputs of this part to be high. And it wants to say that outputs from the generator don't come from the data distribution. So it wants this part to be small. Therefore, it wants to maximize this expression as well. The generator, on the other hand, only comes into play in the second term here. It wants the outputs of the discriminator to be high for its samples. It's trying to minimize this whole expression here. Any questions so far about GANs or this objective?
You mentioned that this works well with CNNs because of some of the statistical properties. Would it work with other classes of neural nets, or are you really leveraging that sort of benefit?
Can you repeat the question?
Yeah, so the question was, can we use this with other types of neural networks, or do we really have to just use it with convolutional neural networks because of their specific properties? I'll actually come back to that question shortly. The short answer is mostly yes. Mostly, it really helps to use convolutional neural nets over other types of neural nets. Okay, so here we have the training objective again here, and we have a proposition that if we fix G, then the optimal discriminator will be given as the data density over the data density plus the generator density. So we can prove that by expanding our cost function at the top here, this minimax objective, into integrals. So this is just by the definition of expectation here. And then to go from this line to this line, we just do a change of variables. When we sample a z from pz and pass it through g, we get a sample from the generator density pg. And so that gets us to this expression in equation 2. And then if we look at the argument of that integral and just do another change of variables here, we have something that looks like a log y plus b log 1 minus y. That's a convex function that has its maximum at a over a plus b, where in this case a is p data and b is p generators. So the optimal discriminator will be equal to p data over p data plus p generator, fixing g. Now if we substitute that expression for the discriminator back into this cost function and do a little bit of algebra, we get a constant plus what's called the Jensen-Shannon divergence between the generator distribution, the data distribution and the generator distribution. And that will have its minimum value of 0 when the generator distribution is exactly equal to the data distribution. So that's the proof that the generator will learn the data distribution. Now, there's been some recent work replacing this Jensen-Shannon divergence with other kinds of distances between distributions, like Wasserstein divergences. And this becomes useful when our models don't have infinite capacity. So we're making quite a few assumptions in this proof that D and G are infinite capacity. Notice I've dropped theta G and theta D. We're just optimizing with respect to D and G directly. We have infinite data, et cetera. And you can imagine replacing with all sorts of other divergences as well. So there have been some interesting papers looking at what happens when you do that. And for example, a bad thing could be replacing this with the KL divergence between PG and P data. That happens to have a bias to learn sort of fairly compact representations for the distribution you're trying to model, which would result in images that don't have a lot of variability, for instance. Okay. And sort of last slide of lots of notation, don't worry, maybe. This is the actual algorithm that's used to train the GAN. So this was presented in the original paper. We start by sampling what's called a mini batch of noise samples, Z1 up to Zm, from our noise prior. We then just select some arbitrary sort of random collection of training points, X1 up to Xm, from our training data set. And then we update the discriminator by ascending its stochastic gradient on theta G here using this cost function. And then we do the same thing for updating the generator. We sample a mini batch of noise samples, Z1 up to Zm from the generator density. And then we update the generator by descending its stochastic gradient on this cost function. So that's the practical SGD training algorithm that's used to learn the parameters of the generator and the discriminator. And like I said, D is trying to make this expression big because it wants X's from the training set to have high outputs, and it wants inputs from the generator to have low outputs. Whereas G just wants to fool the discriminator. It's the gang trying to fool the police here. Okay, so these were the samples from the original GAN paper. In the top left panel, we have MNIST digits sampled from the generator, except for in the far right column with the yellow borders, and those are the closest images in the training set. And the point they're making there is that it's not just memorizing the training set. So those look pretty good. The faces look, sort of okay, and then the bottom two look, kind of weird. But actually, those colored blobs were so incredibly exciting at the time of this original paper in 2014. Like, this was still at least state of the art. Matching what you could do with these stacked RBMs and hybrid Monte Carlo and all sorts of really complicated stuff using an exceptionally simple procedure for trying to learn this distribution. So this was enough to generate a huge amount of interest. And I did mention earlier that that the biases of the neural networks really mattered. These original results were produced using a fully connected neural network. In the following years, people started using convolutional neural networks, and we can see that there's a big increase in the quality of sample generation. And that's strictly through the inductive biases of the model, not the flexibility of the model. Conv nets are less flexible than fully connected nets. But like in many GAN papers, you can see that the tiled images here look pretty small. They're pretty low resolution. And this was sort of a normal thing for a while because high resolution was hard using these GAN generators. But these are the results from the most recent paper a couple months ago on arXiv, and they're really exceptional. These are not real people. These are synthetic people, basically, that were generated just using a database of celebrity photos. So these are samples from the learned distribution over what celebrities look like, basically. So this is really incredible. Like the fact that we've gone from this to this just in a few years, and it's a lot of it has been through better inductive biases in these neural networks. You can also do some of these sort of fun tricks that you can do that you may have seen with word embeddings. Here we started with a bunch of pictures of men wearing glasses, and then we learned a mapping back into z-space to get this as sort of the average z-vector associated with men wearing glasses. And then we subtracted the average z-vector associated with men, added the z-vector for women, and then sampled from small perturbations around the resulting vector, and you get pictures that look a bit like women wearing glasses. So there's actually sort of linear structure that's learned inside this z-space after you've trained the GAN model. You can do something similar here where on MNIST digits, we're just linearly interpolating between different coordinates in z-space, and we see that we're getting different digits. And so this is all done in an unsupervised way. So after training, we get this fairly interpretable, simple structure in z-space. And maybe it's not too surprising because, like most models, at the very end of a neural network classifier, we typically have, a linear layer. And so that means that you're doing some transformation such that your problem basically becomes linearly separable. And so with a GAN generator, if you kind of go backwards through it, it's like an inverted convolutional neural network. So the z-space is maybe getting close to the point where things become basically linearly separable again. Okay, and we can combine with natural language models. So here we have some descriptions. The small bird has a pink breast and crown and black primaries and secondaries, and then out we get these images. And what's really cool about this is, unlike, it looks sort of like a Google image search, but unlike the results of a Google image search, these are entirely synthetic pictures. So these aren't actually pictures of birds. These are imagined, in a sense, from the generator model. In the bottom two panels, though, the results are a bit less convincing. Can someone tell me something that's a bit weird about these samples? I heard something. Similar. Yeah, so someone said they look quite similar, and that's right. So there isn't really a lot of variability. Like if you entered this description, not that you would, into Google Images, and you got this result, you probably would be disappointed. And the reason is, they look weird. Like they look all the same, basically, and not that convincing. And that's an example of a classical pathology associated with GAN training called mode collapse, where the generator collapses most of its mass onto just a few examples in the data distribution and doesn't have enough variability. Here we have another example of mode collapse where we see that as training proceeds, the generator is sampling from different modes of a multimodal distribution shown on the far right, but at any given iteration, it isn't capturing the full multimodal distribution. So it's just cycling between modes. So this has been, the subject of intense sort of modeling efforts in the last couple years, and one of the key understandings for why mode collapse happens can be found by just switching the order of the min and the max. So if instead we're fixing D and minimizing G, then G is just incentivized to put all of its mass where D is most happy, basically. So we could imagine this in the gang example is like, suppose the gang just sort of luckily produces a good-looking $5 bill, and the police says, that looks great, it's fooled us. And then the gang learns, okay, well now I just need to produce good-looking $5 bills, and then I'll win the game without actually, sampling from a full distribution over currency. And so, this is an example of what's called mode collapse, and it can be explained by switching the min and the max. But when we actually train the GAN using that stochastic gradient descent algorithm, it's agnostic to the ordering of the min and the max. So this is sort of what you get sometimes as a result. To remedy this pathology, one often does various interventions. So there's these things called feature matching, where you're trying to basically have samples from the generator match moments of the data distribution. This is reminiscent of another much older approach called ABC, approximate Bayesian computation, a different type of generative modeling. Mini-batch discrimination. So rather than the discriminator operating on a single sample, it's operating now on sequences of samples from the generator. And you can imagine that that would be a good way of identifying mode claps, right? Because any individual sample might be okay. If I just took one of those pictures of flowers, you might have said, oh, well, okay. But if I give you 10 of those, then it's not so great anymore. Similarly, if you were police and you seize some sort of gang member and you open their wallet and you see, 100 $5 bills, you might be quite confused. But if you saw one $5 bill, then, that might be fine. You could also imagine this in maybe the more generic context of trying to do density estimation. And you could suppose that your true density is just some standard normal distribution. And suppose I was trying to give you potential samples from that distribution. If I gave you a sample of 0, you couldn't say that's a bad sample. In fact, it's the most probable sample from this distribution. But if I gave you a sequence of zeros, you could say, no way, that's an impossible draw from that distribution unless the density is completely collapsed around 0. So mini-batch discrimination is another way to avoid mode collapse. There's also label smoothing, where you have the discriminator saturate at, say, 0.1 and 0.9 instead of 0 and 1, which is reminiscent of what people do to try to avoid overfitting. And in fact, this whole phenomenon of mode collapse reminded me of what happens when you try to do maximum likelihood estimation of a mixture of Gaussians for density modeling. As a step towards avoiding such pathologies and representing uncertainty in the generative mechanism for data, we start by just placing a distribution over the generator and discriminator parameters. So this is sort of the easy part. We say that rather than theta g and theta d being deterministic, they're actually random variables. They're drawn from these distributions, given in equation 5 and 6, and alpha g and alpha d are just parameters of those distributions. So we could have something very simple like p theta g given alpha g is n0 alpha g squared I. For instance, those are just hyperparameters. And when we do that, we have a distribution over distributions of data. So we'll unpack what that means. To sample from the generative model that we've proposed, we first sample from our prior over theta g to get some weights of our generator network. We then sample, as before, from our noise distribution. We sample z1 up to zn. And then we form our generator using those weights that we sampled from our prior. And then we pass those z samples through the generator to get candidate samples from a data distribution. We then repeat this procedure if we want to sample again. So we resample theta g, etc. And so the hard part here is then figuring out how to update our posterior beliefs in response to adversarial feedback. So we could imagine initially that we have a fairly broad distribution over the possible values of theta g. So on the vertical axis here, we have p theta g. On the horizontal axis, we have theta g. Let's suppose, we'll just illustrate this as having no real preference for any value of theta g initially. And so let's suppose we sample some value of theta g prime, which is sampled from p theta g. And then let's suppose we use those weights in our generator to produce some candidate data samples. And let's say the discriminator says, no, I hate those samples. That wasn't a good value of theta g. Then we should update our posterior beliefs so that there's a dip in probability around that setting of theta g. And because this is sort of a proper normalizable distribution, some other settings of theta g will become relatively more probable. We can then resample theta g. Maybe we sample over here. We get theta g double prime. And then we generate samples from the resulting generator that we get with those weights. And suppose now the discriminator really likes those samples. It says, yeah, it looks like those come from the data distribution. Then we should again update our posterior beliefs so that there's now an increase in probability around that setting of theta g and a relative decrease for some of the other values. And so we can formalize that procedure by specifying two conditional distributions, one for the generator parameters given the discriminator parameters, and one for the discriminator parameters given the data x and the generator parameters. So in the top equation here, equation 7, basically it's saying that for a particular setting of theta g, if g is sampling images which the discriminator doesn't like, then that'll have a low likelihood signal. So d here is basically being used as a link function to create a likelihood from the discriminator. And this isn't too different from, say, logistic regression, where you choose something like a logistic sigmoid as a link function for discriminative classification. You could have chosen a probit or something else, but it's a design decision to choose a logistic sigmoid. Whereas here, it's a design decision to choose the discriminator as our link function to form a likelihood for updating the generator parameters. In the bottom equation here, equation 8, we just have a sort of a fairly standard likelihood for binary classification. If D is getting inputs from the training set, X, then it's going to want to learn parameters that give you high probabilities. If it's getting samples from the generator, it wants to learn parameters that give you low outputs. And here we have the discriminator prior. However, it goes a little bit deeper than just using the discriminator as a link function to create a likelihood. If we have broad priors, so let's suppose we have no preference for any value of theta d or theta g, and instead of sampling from these conditional posterior distributions and doing Bayesian inference, we instead do iterative optimization, then the solutions that you'll get for theta d and theta g are exactly the same as what you would get using the classical GAN training algorithm. So another way of putting that is map inference in this formulation for Bayesian GANs. If you have a vague prior, corresponds to the classical GAN algorithm, which casts the classical GAN training procedure as like a maximum likelihood training procedure. So this is an analogy that you want to see in Bayesian modeling. Because we're being Bayesian, we want to sort of marginalize everything. So we have a distribution over Z as well. We can write the joint distribution using the sum rule as equal to this conditional distribution on the left-hand side. We can unpack the sum rule using the product rule as we do on the right-hand side of equation 9. And then we can sample from PZ to estimate this integral. So Z is actually conditionally independent of theta d, so this is a fairly simple thing we can do to estimate the sort of distribution of theta g given theta d, but not given Z. We can follow a similar derivation for theta d given theta g. In this case, it's a bit more approximate because we don't have that conditional independency given the data x. So while Z doesn't depend on theta d, it does depend on the data. In an extreme case, if you just have one x, then there's going to be almost a unique Z that gives you that x. Whereas if x is large enough, then it becomes not a bad approximation if you have a big enough mini batch. One of the nice things about this setup is that in this case, P of theta g given Z is actually quite broad when you view it as a function of Z. So almost all of these samples that we get from PZ is going to contribute quite reasonably to this approximation of the integral. Okay, so we wanted to develop this model specifically for semi-supervised learning problems. So in semi-supervised learning, we want to share strength across labeled and unlabeled data to make better predictions. In the figure on the top here, we have a single sample from each of two classes. A white sort of dot and a black dot here. And because we don't have very much information, we aren't going to have a very useful decision boundary to decide how to classify new points. In the bottom panel here, we imagine that we've seen a bunch of other unlabeled points given by the gray dots. And by sharing structure across the unlabeled and labeled examples here, we're able to produce a much more informative decision boundary, which will make much better predictions. So you could imagine, to make this a bit more concrete, maybe one of these is sort of a horse, and one is a dog and is sort of labeled as a horse and a dog, and then you're given a bunch of unlabeled images of horses and dogs, and then through that you just get a better understanding of what it means to be a horse versus a dog, and that helps you classify additional examples. Okay, so to modify the procedure that we presented for semi-supervised learning, it's actually quite a simple idea. We just redefine the discriminator so that instead of outputting a single number between 0 and 1, it outputs a vector of k plus 1 probabilities for a k-class classification problem, where one of the dimensions corresponds to the label from the generator or not. So from the generator perspective then, it's trying to generate samples that the discriminator thinks is from one of the k real classes. So it's just trying to maximize the sum of those probabilities. From the discriminator perspective, it's trying to get the examples that have specific labels correct. So if if there's a label that says this is a 7 or this is a 4, then it wants to get the discriminator correctly labeling those examples. Otherwise, everything is basically as before. It wants the discriminator to be saying that samples from the actual data distribution come from the data distribution. So it's trying to sum this sort of outputs of the discriminator over the k real classes, and it's trying to correctly label samples from the generator. So you could view samples from the generator as kind of like a labeled class, just like this is a 7 or this is a 4 or whatever. And then over here you have just the unlabeled real examples, so unlabeled examples from the data distribution as before. Any questions about this procedure of semi-supervised learning? So what's interesting about this setup is, unlike in the classical GAN setup, where all you care about is the generator after training, all you really care about here is the discriminator after training, because that's what you're going to do to classify new inputs. After we've trained this model, we basically have a discriminator where you can take in any image as input, and it'll give you a vector of probabilities of which classes that input could have come from. And that's what we're going to use for doing classification. And by being able to correctly identify samples from the generator, where the generator is learned in an unsupervised setting, it's actually able to better identify the labels of unseen test examples. Okay, and then finally, when it comes time to make predictions, we just do Bayesian marginalization of samples from the posterior over the discriminator weights. So here we just have a Bayesian model average, the predictive distribution of our neural network, given some setting of parameters, multiplied by the posterior probability of those parameters given the data. So in the procedure we've proposed here, we have a bunch of samples from theta d given everything else, and we use those to do Bayesian marginalization. So these equations aren't specific at all to the Bayesian GAN. This is just a Bayesian model average. Okay, so the next question is how we actually sample from those conditional distributions. To do that, we use this procedure called Stochastic Gradient HMC. It's an MCMC approach, which allows you to use mini batches of data and allows you to use gradient information to make good proposals. And algorithmically, it's actually quite similar to momentum-based SGD, which is really good news because it means that whenever we use SGD to train a neural network, we can also use SGHMC to train a Bayesian neural network. And we won't have a lot of additional computational expense. And all of the empirical insights that we've gained over the years in applying SGD to deep learning also apply to this algorithm for doing inference in Bayesian deep learning. And that's quite important because although the Bayesian approach is often desirable in deep learning, until maybe a few years ago, it's been pretty much computationally inaccessible. And that's really changed with the advent of these types of inference algorithms. So this is, in a sense, made the Bayesian GAN possible and could make Bayesian deep learning in all sorts of other areas also possible. Another point here is that I think that there's a special advantage to being Bayesian in the context of deep learning, even relative to using other model classes. And this is partly because the posterior over the parameters of a deep neural network are often not that well specified by data. So you might see something that's So let's just suppose we're talking about generic weights in a neural network, and we're considering the posterior after we've observed some data. Often it is not really sharply peaked, and it'll have a bunch of broad local optima. And so typically when we train these models, we represent this whole distribution with just a point mass centered around one of the modes. And that throws away a huge amount of information. If the model were more well determined by the data so that the posterior were collapsed around this point, then maybe that's not a bad thing to do. It's not going to give you a very different answer than trying to do that Bayesian model average that I showed on an earlier slide. But if it's very diffuse like this, then you will get a very different answer, even if your prior is quite uninformative. So even if your prior doesn't really tell you very much about what these parameters should be. So this is a case where, even with an uninformative prior, you'll get typically a very different answer doing optimization versus marginalization. Also, in some work on optimization, it's starting to be believed that the reason stochastic gradient descent is good at training neural networks versus BFGS or some of these other more classically appreciated models is because SGD is finding really broad local optima. And if you've converged to a broad local optimum, then you don't need to be as precise about your parameters. Whereas if you had a really sharp optimum like this, then if you maybe even add a few training points or remove them, the location could shift and you could be back at a pretty bad solution. And so if it's true that SGD is finding broad local optima and this is a good thing, then this also means that there's going to again be a pretty big difference between marginalizing that type of optimum versus representing it with a single point mass, whereas there wouldn't be such a difference if it looked like this. Okay, so this is the actual algorithm that we used. The main point on this slide is that it's very much like the classical GAN algorithm, that stochastic gradient HMC is very much like momentum-based SGD plus noise. The noise has a special kind of variance. So a lot of the stuff that we do for training GANs can be adapted algorithmically in a straightforward way to the Bayesian GAN setup. Okay, finally, so this figure. Here we have 6 different panels in the top row, which represent different generators which have been sampled from our posterior over generators. And with each generator, we've generated a bunch of different digits using this MNIST handwritten training, digit training data set. And we can see that the properties of each of these panels in the top row are quite different. So you have different writing styles, writing utensils, etc. And these correspond to different kind of generative mechanisms for the data. Whereas in the bottom row, we have the classical DC GAN trained 6 times. While the images themselves look, reasonable fidelity, maybe even better than the images in the top row, they're very homogeneous. There's really no diversity in the samples. And so this is not sort of capturing the full extent of the data distribution in a sense. Now, if we wanted to produce really high fidelity samples, then indeed we might want to choose one of the modes in this posterior and just generate from that, which is basically what the DC GAN is doing. But by trying to represent the whole posterior, we can actually get much better results for applications like semi-supervised learning, as well as better estimates of uncertainty over the generator representation itself. In this example, we show how the Bayesian GAN can also naturally avoid mode collapse. So we have samples from a multimodal distribution on the left, samples from a classical GAN in the middle, converging to one of the modes. And on the right, we have samples from the Bayesian GAN. In this bottom right figure here as well, what we've done is we've represented samples from the generator, the distribution over the generator weights in a 2-dimensional space to show that we're not only getting samples from a multimodal distribution in data space, but actually the distribution in weight space is multimodal as well, as we've depicted on this diagram here. And so that, in a sense, rationalizes why we're using a sampling approach to solve this problem versus variational or just classical GAN. And we tested the semi-supervised procedure on a bunch of different data sets. And as I mentioned at the beginning, we showed at its best, it could make state-of-the-art predictions with less than 1% of the labels. And it was quite a bit better than what happens if you adapt, say, the DC GAN or the Wasserstein GAN to do semi-supervised learning in a similar way. So being Bayesian, really does make a difference here. It also outperformed ensembles of DC GAN. So this sort of column right next to the Bayesian GAN is essentially everything we could do to make the DC GAN good at semi-supervised learning, including a special ensembling procedure of 10 DC GANs. And even then, the Bayesian GAN tends to outperform that ensemble, and it's all done in a very automatic way. Another thing we see generally is that there's a big gap between fully supervised learning and semi-supervised learning. So you can interpret these plots by comparing the light blue curve here, which is the performance, the accuracy with fully supervised learning, to the darker blue curve here, which is what you get if you use a DC GAN with semi-supervised learning, to the red curve here, which is what happens when you move to the Bayesian GAN. So this is kind of the gap between supervised and semi-supervised, semi-supervised and Bayesian semi-supervised. You can also play a lot more with image generation and again see this type of diversity. I think there's still work to be done in this space. So although there's diversity between panels in samples from this Bayesian GAN, there isn't often a huge amount of diversity within panels. So that's something you could also address by developing different type of generators, by moving to different type of GAN formulations. The Bayesian GAN here is a natural Bayesian generalization of the classical GAN. It's also possible to generalize, say, the Wasserstein GAN and other types of GANs in a similar way by proposing likelihood functions that will give you the sort of analogous GAN if you were to do map optimization. So in terms of future directions, we're exploring different types of approximate inference, really trying to dig deeper into semi-supervised learning, looking at interesting priors over the parameters of the generator and the discriminator parameters. And code is also available if you'd like to try this out for yourself. And there are demos of how to reproduce the results that we have in the paper here. Just as a final unrelated note, I thought I'd mention, since I know some of the audience is very excited about Gaussian processes, we're on the cusp of releasing a new library called GPyTorch, which implements really highly scalable Gaussian processes. And it's publicly available now, will be officially announced soon. And this implements a lot of sort of state-of-the-art methods that we've been developing in my group for scalable GPs, and it can be naturally integrated with deep learning models, et cetera. Okay, thank you.
Question from the audience?
Mm-hmm.
So one of the critiques of Bayesian methods in general always is that it's very sensitive to priors. Are you seeing this as much with this as well? Like, if you choose a very bad prior, does this not work at all? Or is it, how much you have to mess around to actually get these to work?
So one of the advantages of this formulation is it requires less intervention than the classical GAN. So in that mode collapse example I had earlier, we actually had to do a lot to have the classical GAN even perform kind of this well, whereas the Bayesian GAN was fairly automatic. I think choice of prior matters, but it matters less than you think for things like neural networks. So in fact, these arguments that I applied here about marginalization versus optimization would be true even if your prior was just a constant that was scaling the likelihood, because in that case still you have this very diffuse likelihood and you want to kind of represent that whole distribution if you're following kind of what probability theory tells you to do. So I think even with an extremely vague prior, which is basically what we used here, you can see a big difference. Now, I guess this is maybe a bit of a deeper point, but I also tend to view the prior as not just the prior over the parameters, but the prior over parameters in conjunction with the sort of functional form of the model that's using those parameters. So in a sense, both together induce a prior distribution over functions. And because the neural network has a lot of structure that's baked into it, even if you have a really unstructured prior in weight space, you'll end up with a very structured prior in function space. Whereas with, say, a Gaussian process, that would be a disaster if you had a vague prior, because it would be saying that the data were just noise, that it's all uncorrelated. So it depends quite a lot on the functional form of the model as well. At the same time, I think it's an interesting area of research to try to develop more informative priors for weights of neural networks, and something that's largely unexplored.
Well, if there are no more questions. Thank you, Andrew, again.
Thank you.